There was infinite many solutions, right?
Number 1, A
Um,
and B.
Actually, you had said that wasn't parallel. It was a true, or is it not talking about like that equation?
Let's see. Okay, tell me your question one more time.
So I had solved B and neither 6 or -5 worked.
Mhm.
So can you tell by looking at it by looking at it, by not looking at a calculator, can you tell if since there was no solutions, would that have meant that it's a parallel, like just by looking at it?
If there's no solution, your lines are always going to be parallel. And if there are infinitely many solutions, then your line it'll just be one line that's the same.
What can you tell from like looking at A, like since A was true?
So A is asking a different question though. A is just asking, do these two values solve the system? So the system has a solution because these two values solve the system. So this is a solution. Because this isn't a solution, that doesn't mean no solution. That just means this is not a solution to the system.
Okay. I was just wondering if you were able to tell where the lines would go just by looking at like number like A.
Well, you can kind of get an idea just by solving the equation for y and being able to figure out what the slope is. Because if you solve each equation for y, and we did that for both of these, the slope for the first one ends up being -3, and the slope for the second one is -2/3. So since they don't have the same slope, they can't be parallel. And they would also, if they were the same equation, then they would be the same line, and then you'd have infinitely many solutions. So you kind of have to just look at the slope to determine that.
Did you say, you said any of these equations that we were working on, whenever we found x or y, we can put it back in, like once we find y or x, we can put it back in with whatever equation we choose?
Yes, yeah. And so when you back substitute, you should be able to back substitute into either one of the original equations.
I think you had said except for one of them, but I forgot which one.
So the only time you don't want to substitute, and I mean, you only have to be picky about the equation in which you substitute into whenever you're just performing substitution in general. So for instance, down here, when we said y equals 9x plus 5, when we added 9x to both sides, we have to substitute that quantity into the other equation. If you substitute it back into the original, you'll get back a true statement, and then it'll look confusing and it'll look like infinitely many solutions. So in that case, you have to substitute the expression into the other equation. But once you find a value, like we did here for x, then you can take the value that you found and you can sub it into either one of these equations to find y.
Oh, okay.
Does that clear it up?
Yeah, that makes sense.
Okay. Running out of space here. Okay. Did you have other questions, Karen?
I think that's it.
Okay. Did anyone else have questions from the notes or the homework from 5.1 and whatever we started from 5.4, which wasn't much? So no questions.
I have a question.
Oh, yes, go ahead.
For the last page we were on in our notes,
okay,
I realized for number 3 to see like if the answer was linear or nonlinear. You said that if I was confused how you figured that out. Like you found out you solved the equation for y, but why didn't I thought like to solve it, I thought you had to figure out if it was equivalent to ax plus by equals c.
Oh, I see what you're saying. I just thought that in this particular case, it would be easier to show it wasn't linear by showing that it was quadratic. And I thought it was most obvious to show that it was quadratic by putting it into y equals. To me, I thought that that made the most sense. But really what you're looking for, when you're talking about whether or not your equation is linear or not, you're looking to have x and y in separate terms, like they are in the second equation for number 3. And they each need to be just to the first power. So x to the first power, y to the first power, and they're in separate terms. And you don't have any other variables or powers going on. That means that your equation's linear. So the second equation for 3 is linear, but the first one is quadratic because you have x squared. And I contrast that with number 2. Again, you have a situation where the second equation is linear, but the first one is nonlinear because you don't have x and y in separate terms. You have them both being multiplied in one term together. So that makes it nonlinear.
Okay, thank you.
You're welcome. Anyone else questions about that? I'm really glad that you have all these questions that you brought to class, Karen. It's helpful, kind of gets us ready, and if anybody else was confused, kind of helps to alleviate that. All right, wonderful. So last time we talked about systems of equations. We solved some application problems, and we worked on elimination and substitution for 2 equations and 2 unknowns. And we started 5.4. We didn't get too far, but we mostly just talked about what a system of nonlinear equations might look like. Could be like a parabola intersecting a line, in which case you'd have 2 solutions, because remember, you're looking at those intersection points. And then we were asked to sketch a system of nonlinear equations that had 4 points of intersection, and we drew a circle and a parabola. Though that's not the only possibility, but that's one pretty common one that you're going to see here. Then we talked about just being able to tell whether or not you had a nonlinear system from the system itself, and we kind of just recapped that. So just you need to have x and y to the first power in separate terms. And basically, in that case, you'll have an equation that's linear. And I always feel like you can solve the equation for y and get a very good sense of whether or not it's linear also if you're not sure. But for the most part, I mean, whether or not you can identify whether or not it's linear isn't going to make that big of a difference as long as you know how to solve the system, which we're going to do right now. If I can get this thing to, full disclosure, I'm operating on like 3 hours of sleep. Is anyone else operating on like 3 hours of sleep? No, a little bit, Beth. Okay. Always. I doubt that. Although there are apparently people who just don't need as much sleep as others. I don't need like a ton of sleep. I usually get like 5 hours a night, but whew, 3 hours versus 5 hours. Big difference. Yes, I did. I was up and I started to nod off, and then like all the speeches started happening, and then I was like totally fully awake, and I was like cannot go to sleep. But anyway, it was pointless. I should have just gone to sleep because, you know, here we are. I could have saved myself all the trouble and do it all over again. Not tonight. We'll see. I get very into anything politics related. I almost minored in political science. I really enjoy it. All right. Good news too, you guys. I downloaded a trial version of the emulator. So I'm very excited about that. It apparently costs like $90. I had no idea it was that expensive. So, oh well. My trial should last through the semester, so works for you. All right, solving a nonlinear system by the substitution method. So we're going to work on substitution first, and then we'll talk about how to solve these systems using addition or elimination. Step one, and this is, by the way, very similar to the way that we solved our systems of linear equations by substitution. Step one, solve either of the equations for one variable in terms of the other. Step two, substitute the expression from step one into the other equation. No difference here. Step three, solve the resulting equation containing one variable. Step four, back substitute. And step five, check, which again, I can't really enforce. So very similar to what you did in the last section. This time, most of the equations you're going to be dealing with when you substitute are going to be quadratic. But that's fine because we know how to solve quadratic equations. So number four, solve the system of equations using substitution. Now, most of the time, these are going to be pretty obvious as to which equation you should start working with. I'm looking, for instance, at the second equation and thinking I'm going to probably swap. I can rewrite, for instance, this equation in terms of x by just subtracting x from both sides. That's one way of doing this. Another thing you could do, though, is just take your y equals this expression for x and swap it into the second equation. So no matter what you do, you're going to end up with the exact same thing here. But since this is sort of the way we started this out in the last section, I'll just stick with this for now. So we're going to take the second equation in this case, solve it for y, and then we'll plug it in for y in the first equation. So going back to our other equation, instead of using y, I'm going to use negative x plus 8. So on the left-hand side, I have negative x plus 8. And on the right-hand side, x squared minus 12x plus 36. And like I said, most of the time you're going to be getting quadratic equations here. And we solve a quadratic equation by making sure that both sides are set equal to 0. So I'm going to go ahead and add x on both sides and subtract 8 on both sides. And then we'll get this set equal to 0. So we'll have x squared minus 11x, and then 36 minus 8 is what, 28? Equals 0. And now, when we solve this equation, we're going to get two values for x. So we have the two numbers that multiply to positive 28 and add to negative 11 are negative 7 and negative 4. So we'll factor. And then we have two different values for x. Positive 7 and positive 4. Now, be very careful here because I know in the last section you got to the end and you had two answers and you circled them and you said, okay, I'm done, I'm moving on to the next one. But be careful here because you did not find an x equals and a y equals. You found two different x equals. That means that you're going to have two different places where these graphs intersect. In order to find the ordered pairs where this occurs, you're going to have to find y for each of these values of x. Now, you already have an equation for y. You know that y equals negative x plus 8. So substitute in the two values of x that you have to find y. So we have y equals negative 7 plus 8. The negative sign is already in the function. The x is just going to become 7. So that means y equals 1 when x equals 7. So we'll go ahead and put down this ordered pair. That's one of your solutions. And by the way, I feel like now I need to make a special note about this. In the last section, I said you can say x equals and put a box around it, and y equals and put a box around it. And I'm not going to force you to actually write your answer as an ordered pair. It's not a big deal. Here, you're going to have to do that for systems of nonlinear equations because you're going to have two different ordered pairs and two different values of x and two different values of y. So if you just get to the end and circle these two and circle the next two, I don't know which one goes with which. Yeah, I can technically follow your work back and figure it out, but you need to write that down and tell me. So when it's a system of nonlinear equations, you're going to have to write your solution as an ordered pair. And I will try to remember to write that into the instructions. For the second solution, x equals 4, we have y equals, again, negative x plus 8, so negative 4 plus 8. And that means that y equals positive 4. So we have a point at 4, 4. Now, this is a really nice one that we can check on our calculators because we just have y equals some quadratic function in x and y equals a linear function in x. So let's go ahead and graph these in our calculator and verify these solutions. We can always check in our calculator, and that's a lot easier than actually just checking the ordered pairs. Before I do that, does anyone have a question about how I obtained these two solutions, 7, 1 and 4, 4? Okay. All right, let's try out the emulator. I'm so excited. Let's see. I'm going to share my emulator. Maybe. There we go. Okay. Well, it's beautiful, isn't it? Oh, wait. Can you even see it yet? There it is. All right. Go ahead and get into your y equals menu, and we're going to graph both of these functions. I wonder if no, that won't work. Okay. I use my variable button. Okay, so we have x squared, and then minus 12x plus 36. What? I did the x thing again. No. Let's start from the beginning. No. X squared plus 12x plus 36 minus 12x. You guys, I'm falling apart here. Really? All right, the emulator situation is going to work itself out, I promise. X squared minus 12x plus 36. Yes. All right, there we go. And then our other equation is y equals negative x plus 8. I'm going to do this whole thing on the calculator. Okay, now we're going to graph them, and our solutions are 7, 1, and 4, 4. So a standard zoom should be good here. Oh my gosh, look at my key history. Wow, that's insanity. I'm going to clear it because it looks nuts. Okay, so there's our graph. Now, if you feel comfortable with this, you can eyeball it and just see and make sure that this is really what's happening. Another thing you could do is verify the points in your table. So one of the solutions we had was 7, 1. That means that you're going to see that point on both graphs. So if you're looking here at the table on the calculator and you look at x equals 7, you end up getting indeed a value of 1 for both graphs. And that's what you're looking for there. So that's a good way to check quickly that this value is a solution to the nonlinear system, just by making sure that when x is 7, you have the same y value for both of them. And then the same thing should be occurring at 4. So when x is 4, y is 4 for both equations. So you can tell that that has to be the solution. You did a good job. If you're not sure, you can always calculate the intersection. This one I'm not used to doing on this. Let's see. think I can, oh, I'll just do it the way I would normally. There we go. And I know I'm looking for at least x equals 4. That's why I'm going to the right. All right, so there's the cursor. I'm going to put it on right about where I think the intersection is. I don't even know if you have to do that. You might be able to just say enter, enter, enter. And you do indeed get an intersection point of 4, 4. And then you could do that again to verify the point at 7, 1. Questions about how to check this in your calculator? So you have a couple different ways there. You can eyeball it, you can look at the table, or you can actually use that intersection feature. This is so much better than me trying to like get the calculator screen to show up. I'm so happy right now. Do you guys like the emulator? Yeah. Oh, sorry, I'm missing things on the chat. How's this happening? Sometimes it beeps and sometimes it doesn't. How do you know the 7 goes with the 1? Emulator is cool. The 7 goes with the 1. You mean from my work with the algebra, Chase, or do you mean based on what we did in the calculator? The algebra. Okay, so I'll go back to the math for that. Before I close the emulator out for now, does anyone have a question about the calculator? One of the things I also like about the emulator is that it does capture the keys that I entered. So if you're like, wait, what button did she enter to get this? You can see it in the key history, except when I press like 1,000 keys to enter one function. That's crazy. Okay, so going back now to my window. Okay, so I know the 7 goes with the 1 because when I used x equals 7 from when I solved this system, and I back substituted it into the other equation, I ended up getting a value of y equals 1. So that's how I know the 1 goes with the 7. And then when I back substituted a value of 4, I ended up getting also a 4 to pop out. That's how I know that they go together. Okay, awesome. You guys are so helpful. Let me see if I can make this thing beep. I don't like when it doesn't beep at me. Oh, it was beeping so well last time. I don't know. It's a mystery. Okay. Anyway. All right. Let's do another one. This one is x squared plus y squared equals 113, and x plus y equals 15. Now, the second equation is clearly linear, but the first equation is not linear. Does anybody know what type of equation or what type of graph this first equation represents? Can you remember? Think back into the recesses of your memory. What type of graph would be represented by x squared plus y squared equals 113? Oh, maybe it's been a long time. Let's see, on my chat that's not flipping at me. It is not quadratic. Oh, circle. Yes, Gian. Yes, a circle. Yes, Simon, Gian, circle. Yes, absolutely. It is a circle. It is not quadratic. If it was quadratic, you would have a y equals x squared, blah, blah, blah. It is actually a circle. The x squared plus y squared equals r squared formula. And we're going to be talking more about circles today. These ones are a little bit trickier to graph in your graphing calculator because remember, your graphing calculator graphs functions, and a circle is not a function because it does not pass the vertical line test. But there is a workaround that I'll show you because it is important to know how to use it. I don't want you to feel crippled just because you have the graph of a circle. So yeah, because it's a circle and because we're intersecting it with a line, we're expecting there will be 2 intersections. Absolutely. Yep. So let's take a look here and see what happens when we use substitution. And, you know, I always solve for y. You can technically solve for x if you want to. I just feel like, in general, I like to solve for y. I don't know why. I don't know why I solve for y. Y equals negative x plus 15. All right, so we're going to substitute this value for y into the first equation. So I have x squared plus. Now, be careful, because when I substitute y equals negative x plus 15 into this equation, it's going to be getting squared. So I have to put parentheses around it. Otherwise, the whole thing's not going to get squared. So I'm going to put in negative x plus 15, quantity squared, equals 113. Now we're going to simplify. Now remember, when you're taking a binomial is a two-term polynomial, and you're squaring it, you must FOIL it out. You cannot distribute the exponent to both of your terms. This is not x squared plus 225. You'll be missing a linear term there. You must FOIL it out. So I'm going to write this out the long way. It's negative x plus 15 times itself. It's a very common mistake that students distribute the exponent. You can't do that. All right, so go ahead and FOIL. Negative x times negative x is positive x squared. Then you have negative 15x minus 15x, which is negative 30x. And then 15 squared is 225 equals 113. And now again, you're looking at a quadratic equation. And to solve a quadratic equation, you need to make sure that you have 0 on one side of the equation. So let's go through and simplify and move everything over to one side. So we'll have 2x squared minus 30x, and then you'll take 225 and subtract off the 113 to get to 112. Now, if I were you, I would notice that you have 1, 2, 3 terms, and they all have even coefficients. The last thing you want to have to do is use the quadratic formula if you don't need to. So go ahead and divide every term by 2, or just whatever you need to do. Divide the whole thing by 2 and get rid of that. Think about it as factoring it out. Whatever you have to do, divide by 2, and then you'll get a new equation. X squared minus 15x plus, what is 112 divided by 2? 56 equals 0. 0 divided by 2 is still 0. And now you're going to be looking for numbers that multiply to give you 56 and add to give you negative 15. So if you're thinking about these numbers, you're probably thinking negative 7, negative 8. And then you get x equals 7 and x equals 8. So really, the only new thing we've done here is we just did a substitution. And once we got to this step, that's it. Everything else was review from the first week of our class. Are there any questions about how we obtain these two values for x? All right, so we have an x equals 7 and an x equals 8. So we need to find the corresponding y value in each case. So let's look up when x equals 7, y equals negative 7 plus 15. So I'm just using this equation for y and then just popping in my value of x. We get y equals 8. So that gives you an ordered pair Put 7, 8. And then you have another value of x, and that's a value of x equals 8. So when x equals 8, y equals -8 plus 15, which means y equals 7. That gives you a point at 8, 7. Which I know seems odd and weirdly coincidental, but you're going to see why you have this behavior when you look at the graph. Before I show you how to graph this, does anybody have a question about the solution? Because this is really the important thing. To graph a circle, or let's just say to graph x squared plus y squared equals 113, you're going to have to put this in your calculator, which means you're going to have to solve for y. So subtract x squared from both sides. And then when you solve for y, because remember, you're not looking for y squared, you're looking for y. Anytime you take the square root of both sides of an equation, you have to apply the plus or minus sign. And if you want, you can switch the order of the subtraction just to make it easier to enter it into your calculator. I don't know if it'd be easier, one less button to push, I guess. So this is two different functions. This is y equals the square root of 113 minus x squared, and y equals the negative square root of 113 minus x squared. So this is what you enter into your calculator. And this just graphs your circle. You're also going to have to graph this linear equation, y equals -x plus 15. Before I move to the emulator, does anyone have a question about how I got these two functions? Okay, so to graph a circle, you're going to graph it using this function and this function. And if you're not sure why or what that means, well, you're going to see it in a second. You'll understand. Let's see. All right, so go back to your calculator. And we're going to enter, I guess it doesn't matter which one you enter first. I guess I'll do the circle first. The square root. Oh, you know what? I'm going to clear this. Just here, I'll clear that too, so that you can see all my keystrokes. The square root of 113 minus x squared. So that's one function. The other one is the negative, don't use minus, make sure you're using negative, square root of 113 minus x squared. And those two together will graph your circle. And then the linear equation that you're going to graph has to be written in terms of y. We have y equals -x plus 15. Now, what's interesting is as we enter these into the graphing calculator, you can see on my screen the pieces of this graph that are coming together. Y sub 1 is going to be in blue, and you can see that's the top half. And y sub 2 is going to be in red. There's your bottom half. If I click away, it'll probably graph the line. Maybe not. I'm not used to how this does its thing. And you might be looking at this and saying, that doesn't look much like a circle. Well, it is a circle. It's just that your window is kind of pulled out horizontally. So, oh, now it doesn't like my syntax. I didn't even do anything. All right, well, let's just graph. Is it my negative sign? It is my negative sign. I'm just wanting to fix my negative sign. Go. I think I used my keypad. I don't know what I did. That's why I was getting a syntax error. Okay, now graph. You know, it keeps converting my negative sign to a minus. I just went and fixed it. Oh, now it's back. Okay, I'm just watching what's happening here. All right, everything's okay. Now, you might be looking at this and wondering, it doesn't look like you have 2 points of intersection here. What's occurring? Well, you're going to have to zoom in a little bit in order to see what's happening. If you're not sure how much to zoom in, well, I don't know, just kind of eyeball it. You know, whatever's happening has to be happening right in here. So I'd maybe look at values of x that are, I don't know, they'd have to be larger than 5 if we're looking at values that are between 7 and 8. So maybe I'll go from like 5 to 9. And then again, I'm looking at values between 7 and 8. So maybe I'll also go from 5 to 9 on the y-axis. So I'm going to set my x min to 5 and my x max to 9. And my y min I'll set to 5 and my y max I'll set to 9. And we'll see what we get. Sometimes you have to play around with your window to really get a good picture. We'll see. This will get us close. But, you know, actually, I like how this emulator gives me a little preview, because now I'm already kind of thinking, this is not good enough. But really, it should be giving me a y min of 5. Why is it showing me what's underneath the axis? I don't know. This preview is whatever. Okay. So it's close, but it needs to be even closer. So I'm going to narrow this in a little bit because I need to see that there are 2 distinct places where you have an intersection here. So maybe I'll even narrow my window to 6 instead of 5 and see how much that helps. I'll make the x and the y mins 6. I don't know. We'll see. My whole point in doing this is I want you to be able to get a good enough picture so that you can use the calculate menu to get those points of intersection. I mean, this might be close enough just to double check in your calculator, but you can also go to your table. 7, 8, 8. Oh, and I'm actually really glad I mentioned the table now, because if you're looking at the table, don't forget that this y sub 2 is the bottom half of your circle. The intersection's not actually occurring on the bottom half of your circle. So you don't need to think about these y sub 2 values. The negative value that you put in for your circle is the bottom half. Focus on the top half. When x is 7, y sub 1 is 8, y sub 3 is 8. That's the point at 7, 8. When x is 8, y sub 1 is 7, y sub 3 is 7. That's what you need. Remember that your y sub 2 is just that bottom half of the circle. Nothing is happening there. Now, you graphed it because you didn't know and you were trying to get a good idea, but now you do. And when you're looking at the table, you can negate this y sub 2 column. So you can do that in the table. And then if you want to play around with the calculate menu, be my guest. I feel like mostly I wanted to do this in the calculator just to show you how to graph a circle. And if you don't believe me that it's a circle, you can always go to zoom square, which is zoom 5. I think you have to do 6 before you do 5, otherwise it gives you a weird window. So I'll do 6 and then I'll do 5. And we might even have to zoom out a little bit, and that's okay. So we'll go back to zoom 5, which is zoom square. And that will make it a little bit more obvious that what you have is a circle. And if you're wondering, what are these gaps that are occurring here at the x-axis? Why is that happening? Well, the gaps are because at that point, remember your calculator can only graph functions. And at this point, your graphing calculator is saying this looks like a vertical line, or at least it's going to end up that way if I try to graph it, and it can't graph vertical lines. You only have so many pixels on your screen. So it leaves a gap there because it can't graph the vertical line. All right, so that was a lot of information there with the calculator. Does anybody have a question on number 5 or how to do any of this in your calculator? Let me check the chat here because I didn't hear it beeping. Karen used the zoom button. Yeah, you can use the zoom button too. The only thing is sometimes you have to recenter your zoom. Otherwise, it's going to just give you a general zoom. But yeah, you can also do a zoom in, a zoom out. You can play around with the zooms and the windows at will. Play around with the calculator features. Anyone else? Questions or comments? Okay, now number 6 is a little different. Get this back up here. So number 6 is nonlinear. The difference, though, for number 6 is that you don't have a situation where you have a quadratic equation or a circle or some sort of x squared term in the system. So it looks a little bit different. But we're still going to use substitution. So I'm still going to start out by letting y equals negative x plus 5 for the second equation. So just rewriting that to an equivalent form by solving for one of the variables. And if you prefer to solve for x, solve for x. Whatever you want to do. And then once you get this value for y, go back to your first equation and sub it in. So you have x times y. Well, now you have x times negative x plus 5 equals 6. Now this is still a quadratic equation, but this original equation that you had was not quadratic in form. Now it is. For a quadratic equation, we need to make sure that we have one side set equal to 0. So we have negative x squared plus 5x. And if I were you, because you have a negative x squared, I'd probably make that positive and bring these two left side terms over to the right. You don't have to, but I think that would be an easier way to do this. So I'm going to add x squared to both sides and subtract 5x from both sides. And I will end up with x squared minus 5x plus 6 equals 0. This is that quadratic equation that everybody solves wrong because they take the wrong factors. So remember, you're looking for numbers that multiply to positive 6 and add to negative 5. So in this case, negative 2 and negative 3 will add to negative 5. So don't use negative 6, positive 1, because those don't multiply to positive 6. Be careful here. So like we have x minus 2 times x minus 3 equals 0. That means x equals 2 and x equals 3. And I will find the corresponding y values by back substituting into the first equation. Are there any questions at this point? Wouldn't it be -6? No, because I moved the left side terms over. The 6 didn't move. So it was 6 up here. It's still 6 down here. And then all I did was I moved the left terms to the right. So the 6 stayed positive. Yeah, I know. That's always tricky whenever there's a lot of stuff that's moving at one time. Yes, thank you for asking. I am so tired. Who knows? I could have done something crazy. So gotta watch out. Okay. So we have x equals 2 and x equals 3. And then we'll just go back here. When x equals 2, y equals -2 plus 5. So y equals, or I'm sorry, -x plus 5. So -2 plus 5. Y equals 3. That gives me an ordered pair at 2, 3. And then when x equals 3, I have y equals -3 plus 5, which is 2. And I know it seems odd because you've seen this happen twice now. You had 7, 8, 8, 7 in the last example, and now you're saying 3, 2, 2, 3. It just happens. It's coincidental. It's just a thing. I'm not going to do this one in the calculator, but you can graph this in your graphing calculators. If you wanted to put this in your graphing calculator, you could solve it. You could take x, y equals 6 and solve it for y by dividing out x on both sides. So if you wanted to graph x, y equals 6, you would just graph y equals 6 over x. And then you could find the intersection between this function and the diagonal line. Now this is that reciprocal function. You are seeing it intersect in 2 places. So you would only really need to look at that first quadrant because this is going to graph itself in 2 pieces. Any questions on number 6? Okay. We sure? Okay. Let us solve a nonlinear system using the addition method. Now, like I said before, a lot of times you're going to know just by looking at the equations what method you should use. Now, looking at number 7, this is a prime example of when you would want to use the addition method. The reason is you can only combine terms when they're like terms. And here you have like terms. You have an x squared and an x squared. You have a y squared and a y squared. You have a constant and a constant. These are all terms that you can combine. That's why the addition method is perfect for something like number 7. You're looking for those like terms. With something like number 5, you don't have that. You cannot use the addition method with something like number 5 because if you wanted to add from top to bottom, you would just have x squared plus x. That doesn't help you at all. Y squared plus y. You're just introducing more terms there. So this is not a place where you can use the addition method. So with nonlinear systems, you don't have quite as much, you don't have quite as much of your own free will here to just do whatever you want willy-nilly, just with picking a method. The equations themselves will lend themselves better to one method or the other. And again, this you definitely could not use addition with here on number 6. Same idea with number 4. You kind of have to use substitution with the problems on this page. And in the same vein, you wouldn't be able to use substitution here very easily at all. You'd end up in a pretty big mess because you'd have to solve for a variable. I mean, I guess technically you could solve for y squared instead of y and substitute it in. That's a possibility. But as long as you have like terms, you're thinking that you're going to use the addition method. And it works the same way that it did for linear equations. So you're going to rewrite the equations so that they're an ax squared plus by squared equals c, if they're not already. You might have to multiply one or both equations by some sort of constant in order to get the additive inverses that you need on that as your coefficients. Steps 3 and 4, add the equations and solve for the remaining variable. And step 5 is back substitute, and then find the value for your other variable. So you're going to see how this works. I think it's pretty straightforward as long as you understood how to work on addition with linear equations. The most important thing is knowing when to use which method here, because like I said, you cannot just pick one at will. In some cases, one's going to be much easier than the other, and sometimes you won't be able to do one versus the other. All right, so I'm looking at my coefficients here. I want them to be the opposite, basically, of each other. So I want to have, you know, like a 3 and a -3, or a 5 and a -5. Well, I don't have that. But I do have opposite signs on the y-squared, so it's not a big deal. But if I don't have to worry about multiplying through by a negative, then I don't want to have to worry about it, because sometimes I forget to multiply every single term by the negative. So I would like to stick with eliminating y-squared just because they already have opposite signs. Now, most of us, I think, see 3 and 5 and automatically think, okay, let's turn those into 15s. I agree. Let's take equation 1 and we'll multiply it by 5. And we'll take equation 2 and we'll multiply it by 3. And we want these to have opposite signs, so we're going to multiply them both by the positive values for 5 and 3. Every single term, don't forget about the constant. So 2 times 5 is 10. -3 times 5 is -15. And then 19 times 5, or -19 times 5, is -95. And then for the second equation, you have 9x squared multiplying by 3, so plus 15y squared equals, and then 57 times 3 is 171. Okay, so now I have a situation, double check, make sure you multiplied everything that was supposed to get multiplied. But we have a situation where the y-squareds have opposite coefficients. This is exactly what we want. So now we'll use the addition method by adding from top to bottom in each term. So 10x squared plus 9x squared is 19x squared. The y-squareds in this place cancel out. -15 plus 15 gives you 0. Then you have -95 plus 171 gives you positive 76. Be careful with your signs here. A lot of times people will miss a negative sign, and then that throws off the rest of your answers. So just be very careful. And then 76 divided by 19 is 4. So we have x squared equals 4. Now, don't forget that when you take the square root of both sides, you need to use a plus or a minus. So that means x equals plus or minus 2. So that means I have 2 different values for x. X equals -2, x equals +2. Sorry, Ashley, I totally didn't see your question until just now. Did you still have a question, Ashley? Okay. So last time in 5.1, we talked about how to use the addition method. So I'm just applying that now for nonlinear systems of equations. Okay. So Now I'm going to go through, and it's a little bit harder anytime you're using the addition method to back substitute, but it's not the end of the world. I'm going to say, let's let x equal -2 first. And then I'm going to pick one of these equations. It doesn't matter which. I guess I'll stick with the first one. And I'll back substitute and solve for y. So a little bit more work here for finding the other variable. So I'm going to use equation 1. And this is arbitrary. I just picked it. Doesn't matter which one you use. So I have 2 times -2 quantity squared. Don't forget your parentheses, because -2 squared is not the same as -2 squared. Not the same thing. Minus 3y squared equals -19. And then we'll solve. -2 times -2 is +4, times 2 is 8. -19 minus 8 is -27. Y squared is 9, and y equals ±3. Now, don't be thrown off by this, because you're like, whoa, 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 wait a second. X is -2, and now I have 2 different values for y. Yes, you're going to have to start recording all of this information. And when we get to the end here, we'll talk about why we have this situation occurring. But we had x equals -2, and we had 2 different values for y. One of them was +3, and one of them was -3. So those are 2 solutions, but we're not done yet. These are the 2 solutions that we have when x equals -2. We also have to look at what happens when x equals +2, this other value that we found. Now we're expecting 2 more solutions. And again, I'm just going to, for consistency, use equation 1 with x equals +2. And I'm going to get something very similar. Same exact values for y. It doesn't mean you did something wrong. It just means that we squared the value, and when you square it, it's going to come out positive either way, here and here. Now you have 2 more solutions. You have 2 +3 and 2 -3. Does this mean we have 4 points? Yes, Beth, absolutely. This means that our graphs are going to intersect in 4 different places. Let's see, you're going to have a much harder time in this situation solving for y. You absolutely can graph them if you would like to graph them. Does anybody know what type of equation? Well, these are 2 different types of graphs. Does anybody know what type of graphs we'll get for equation 1 and equation 2? What do you think? There are 2 different types of graphs. If you don't know, it's okay, because we're going to learn about it in chapter 7. Just wondering if anyone knows. Simon says ellipse. One of them is an ellipse. That would be the second one. The first one is a hyperbola, because it's got a minus sign. And that's okay if you don't know that. I don't expect you to know it. We're going to talk about these in chapter 7. So they will intersect in 4 places. And basically, you'll have a situation that looks something like, I don't know, anything like this. Hyperbola and an ellipse. Something like that. But again, you don't have to know that now. You don't even have to know how to graph it now. You just have to know how to solve the system of nonlinear equations. Yes, the only difference is the minus sign. The ellipse is a fun oval. Yeah, I know. Students are always like, it's just an oval. Technically, it's not, but it looks like an oval. Yes. Okay, any questions on number 7? All right, number 8, I'm going to help you start, and then I want you to finish it. So number 8, the first equation is a circle. And if you're wondering, well, why is that equation a circle, but this one is an ellipse? It has to do with the fact that in number 7, the coefficients were different. In number 8, the coefficients are the same. That's a circle versus an ellipse, which we will talk about in chapter 7. And then the second equation is definitely an ellipse. You're going to want to rewrite the second equation, though. If I were you, I would not want to be dealing with these fractional coefficients. Yes, that's the distinction, Beth. So if I were you, I would go ahead and multiply through here, just because you don't want to have to worry about these fractional coefficients that are occurring. If you want, you can just multiply 64 and 9. Really what you're looking for is the least common multiple between the two. So for instance, 64 times 2 is 128, but it doesn't divide, 9 does not divide 128. So you'd kind of go through your list. If you want, your calculator actually has a function. You probably won't use this a lot. Look at, I'm so old school. I have this emulator, but it's such a pain to keep switching back and forth. If you hit the math button, you can go to number, and it will, number 8 is for LCM. So math, number, LCM, and you can actually put in the 64 and the 9, separating them with a comma. And it will tell you that the least common multiple is 576. Now, if you don't remember how to do this, I'm going to remind you right now. You're going to multiply each side of the equation by 576, or each term, I guess. Well, we'll say multiply each term by 576, which is the LCM, to clear the fraction. Now, this you should have done in your previous algebra class, this whole clearing the fraction business, but if you don't remember, I wouldn't be surprised. It's been a long time. Oh, the difference between an oval and an ellipse? I don't know. I just know that they're different. I think technically the shape is different. I don't know. I'll have to look it up, but there is a distinction between the two. So let's multiply each term by 576. Which looks kind of like this. And you're going to have to do this a couple of times on your homework, so get used to it. 576 divided by 64 is 9. So you get 9x squared plus 576 divided by 9 is 64. And then on the right-hand side, you have 576. Now, I know that those values aren't necessarily desirable to you. However, look at the coefficients in your first equation. To use the addition method, you don't really have to do much. You can multiply the first equation by -9 or by -64. I'd probably choose the smaller number, though. I'd probably multiply the first equation by -9. But you go solve this and see what you get. How did I put it in the calculator? See, this is what happens when I don't use the emulator. To find the LCM, then I did the math button. And then I scroll to the right to the number column. And then I hit number 8 for LCM. And then I entered the two values for which I wanted to find the least common multiple, which is also your LCD. And I separated them with a comma. You can always just multiply 64 and 9. That's not always going to be the least common multiple. In this case, it is, but it won't be the least in every case, but that's okay. You can just further simplify it. Did I answer your question, Ben? Yes. All right, now you guys get cracking. I also want to remind you that your drop date is Sunday. I know I told you that on Monday. I'm just letting you know again, in case you wanted to drop with the W. I didn't want you to get all upset that you missed your window. That does not mean I'm encouraging anyone to drop. It is a decision that you need to make. Okay, so the way I suggested starting out was taking equation 1 and multiplying the whole thing by -9. This is a multiplication sign, not an X. And then adding these two equations together. In this case, we're eliminating x squared. You'll have 64 minus 9, which is 55. Y squared equals 0. And if you did this and you thought, okay, what happened? What did I do wrong? This is not right. Not necessarily. I know it's a weird result, but that does not mean that you did this incorrectly. It's just different. Does anyone have a question so far? I'm not sure how far you got. We probably got here and then got confused. Okay, so if we got the result of y equals 0, you pick, we're going to back substitute. I'm going to go with the first equation, x squared plus y squared equals 64. So that's equation 1. Then we have x squared equals 64 and x equals plus or minus 8. So I have 8, 0, and negative 8, 0. Is the intersection between my circle and the ellipse. So you might be thinking, well, a circle and an ellipse, wouldn't they intersect at 4 points? Not necessarily. It depends on where that circle is intersecting the ellipse. I don't know. You'd have to actually graph this out, but you've got this circle that's centered here at the origin. And then you've got the ellipse, which is also centered at the origin. Let's see. Gosh, it's been a while since I've had to graph ellipses, but actually, you know what? Let's look at, I think we should revisit this when we get into chapter 7 with graphing it. For now, let's leave it for now because you're not going to be expected to graph this right now, and I don't want to confuse anybody. Does anyone have a question about the ordered pair solutions? No. Okay. Wonderful. Okay. Let's do an application problem here for nonlinear systems. A person at the top of a 600-foot tall building drops a yellow ball. The height of the yellow ball, this is so weird. The height of the yellow ball is given by the equation h equals negative 16t squared plus 600. So the height of the building is this initial height, 600 here in your position function, where h is measured in feet and t is the number of seconds since the yellow ball was dropped. A second person in the same building, but on a lower floor, that's 468 feet from the ground, drops a white ball 1.5 seconds after the yellow ball was dropped. The height of the white ball is given by the equation h equals negative 16 times the quantity t minus 1.5 squared plus 468, where h is measured in feet and t is the number of seconds since the yellow ball was dropped. Find the time that the balls are the same distance above the ground and find this distance. This problem is super wordy, and I think it can be very intimidating just because there's a lot of information that's being given. And that's really unfortunate that a lot of the application problems that you see sometimes are not nearly as complicated as they sound. Look at what the question is asking. Find the time. Remember, the time is measured as t, the number of seconds. That the balls are the same distance above the ground. Now, the distance above the ground, you were told in both instances what that was. Look at your second sentence. The height of the yellow ball, the height is the height above the ground, is given by h equals negative 16t squared plus 600. And then you were given the same information about the white ball. The height of the white ball is given by h equals negative 16 quantity t minus 1.5 squared plus 468. So you're looking for the time when the balls are the same distance above the ground. And when they're the same distance above the ground, that means the same height. So we're looking for the time t when the balls have the same height. And the height of the yellow ball is negative 16t squared plus 600. And the height of the white ball is negative 16 times t minus 1.5 squared plus 468. So if you're looking at what happens when the heights, if you're trying to figure out the time when the heights are the same, set the height functions equal to each other and solve for t. Now these are both quadratic functions. If you're trying to solve for t, you're going to have to make sure that you simplify. The first thing you're going to have to do here is FOIL this t minus 3/2 squared. Before I do that, does anybody have a question about this equation? Okay, so what I'm really trying to do here as I go through these application problems is just to kind of teach you how to break down the wording. Okay, so the left-hand side is going to stay the same. On the right-hand side, and since I'm going to FOIL this, I don't know, maybe I'll leave it as a decimal. I like to change to fraction, but whatever. So this is really, remember, I'm looking at here t minus 1.5 times t minus 1.5. That's what I'm looking for here when I square t minus 1.5. So I have t squared, and then minus 1.5t minus 1.5t is minus 3t. And then 1.5 squared is 2.25. And then plus 468. And then we'll keep simplifying by multiplying through. So go ahead and multiply into that quadratic expression. And then what we're going to do is combine like terms and simplify and move everything over to one side of the equation. Since it's quadratic, we want one side to be set equal to 0. So I'm going to add 16t squared to both sides and look at what happens there. And then we'll subtract 600 from both sides of the equation. So now when I added the 16t squared to both sides, well, now I have additive inverses and both of them are gone. But I still do have 48t, and then I have negative 36 plus 468 minus 600 equals negative 168 equals 0. I know we spent all that time into getting it set equal to 0, and we don't even have a quadratic function anymore because our quadratic terms went away. So let's go ahead and simplify and solve. Now this is good, by the way, because you can tell already that t is going to be a positive value. If t comes out negative, that's bad. T cannot be negative, it's time. We have 168 divided by 48, and you get t equals 3.5. Don't forget your units. You were told that t was time measured in seconds. All right, now we still have another question to answer. Before we do that, does anybody have a question about how we solve for the time t? All right, the other thing we were supposed to do was, let's see, so find the time t when the balls were the same distance above the ground and find that distance. That means find h when t equals 3.5. And that is what we will do next. So you have two different functions for h. They're the same at 3.5, so you pick which one. I'm going to choose h equals negative 16 t squared plus 600 because that one seems easier to me. And then we'll evaluate that at 3.5. So negative 16 times 3.5 squared plus 600 is 404 feet above the ground. And again, this answer should make sense to you. So h represents the height above the ground at the time when the balls have the exact same height. So someone drops from 600 feet, the yellow ball, and then someone drops from a lower height of 400 and whatever it is, 468 feet, the white ball. And at some point, their height is the same. It happens at 3.5 seconds, and that means it happens at 404 feet. So if you got an answer like 900 feet, well, that can't be because they dropped the balls from the building, and it cannot be that the ball went up and it went higher than the point at which it started. And you probably wouldn't expect it to be like too low to the ground. It shouldn't be negative. So you can kind of get a good idea here for what type of answer you're expecting. Okay, questions on number 9. Wonderful. Then let's talk about systems of equations and inequalities. Now, don't forget, we're going to be starting 6-1 on Monday. And the notes that you have for 6-1 and for 6-2 are technically the key. If you don't care, fine. But if you like to write your notes, please make sure that you copy out the notes for 6-1 and 6-2. I can't have them sent to you, and it would cost me a fortune to do it. It's just not worth it. And the school is, I don't know, it's very confusing. It's a very confusing situation, unfortunately. Okay, so 5-5, we're going to talk about inequalities in 2 variables. And you have talked about these before. It's been a while. You might not have talked about nonlinear inequalities, but you have talked about systems of linear inequalities. A solution of an inequality in 2 variables, x and y, is an ordered pair of real numbers such that when the x-coordinate is substituted for x and the y-coordinate is substituted for y, we obtain a true statement. Each ordered pair solution is SAD. Yikes. SAD to satisfy the inequality. The graph of an inequality in 2 variables. Oh, how did I miss all this stuff happening in the chat? My cursor was on top of the little green thing. Ay, ay, ay. How did you get negative 9x minus negative 9y? Was that like a long time ago, Ben, that you asked me that? It was. Now I know where it came from. Sorry. My mouse was on top of the little green thing that says that I have a chat. I don't know why it's not beeping at me today. This is very, very inefficient. Let's go back. It's a Google Meet problem. It's got to be. I've done nothing different. How did I get negative? Oh, how did I get negative 9x minus negative 9y squared? Oh, x squared, y squared. I took the first equation up here and I multiplied every single term by negative 9. So the whole point was for equation 2, I had a coefficient of 9 on x squared. I wanted to get an additive inverse for equation 1 so that when I solved this using elimination, oh yes, Simon, my speakers are on. I could hear Karen the whole time she was asking questions so that I could get this to cancel out. Yes, my speakers are on. I double checked. So what I did was I went to the first equation then and multiplied the whole equation by negative 9. So that's what you're seeing here is the first equation multiplied by negative 9 so that I could get these two terms to add up to 0 and I could eliminate. Does that answer your question, Ben? Yes. Okay. Sorry, I was super late on that by like a lot. What else did I miss? Quarantine feels like negative time. I know, but then it's like time keeps going and then you're like, wow, like my whole life is passing me by and I'm not even doing anything, just sitting around my house. Like my daughter is going to be 2 in February. Like she doesn't even know that other kids exist. Like this is horrible. It's really horrible. It's not that bad. She goes to the playground a lot, but all the kids are like 5 and she doesn't understand that there are little kids too. Anyway, I know it's unfortunate. Okay. I know she lives probably a really charmed life, so I shouldn't feel too bad. Okay, back to this. All right, graphing a linear inequality in 2 variables. 1, replace the inequality symbol with an equal sign and graph the corresponding linear equation. Now we're going to graph a solid line if the original inequality was less than or equal to or greater than or equal to. And by the way, if you don't know what this is, it's going to come rushing back at you because you have done this before. Draw a dashed line if the original inequality contains less than or greater than. So this one's got the equal to in it. That means solid line. If there's no equal to in it, that means you're drawing a dashed line. Then we're going to choose a test point. And I'm going to go through this with you so you will understand how this works. But we're going to graph the inequality. We're going to choose a test point. And depending on whether or not we get a true statement with the test point, we'll know which region of the graph to shade. So let me show you how this works. First of all, we're going to graph 4x minus 2y is greater than or equal to 8. And I'm going to start out by graphing this one using intercepts. Now, I'm going to graph 2 ways here. If you find that the coefficients of x and y are both factors of c, if you're written in the form ax plus by equals c, if your 2 coefficients are factors of the constant, then I would use intercepts to graph the equation. It's much easier. If you're using intercepts to graph, remember that we said to, in step 1, replace the inequality symbol with an equal sign. And then to graph by using intercepts, you're going to first let x equals 0 to find the y-intercept. Let x equals 0 to find the y-intercept. Now, if x equals 0, then this whole term, 4x, goes to 0. and you have negative 2y equals 8 and y equals negative 4. That's your y-intercept. Plot it on the graph. Y equals negative 4. And if you're wondering why the heck is she doing this, it kind of just depends on the way the equation is given. I feel like graphing with intercepts can be very, very easy, much easier than solving this equation for y and graphing using the slope and the y-intercept. Now, let y equals 0 to find the x-intercept. And then we'll get one more point, and all we need to graph a line are 2 points. Now, if I'm letting y equals 0, then the term negative 2y is going to go to 0. And all I'm going to have left is 4x equals 8. And that simplifies to x equals 2. So x equals 2 is right here. That's your x-intercept. 2 points, that's all you need to graph a line. So go ahead and connect those with a nice straight line. Try to keep that slope going to the best you can to make it look nice. Now, normally I go through this whole rigmarole where I'm like, oh shoot, I forgot it's supposed to be a dashed line, and I have to go through and erase. In this case, it was not supposed to be a dashed line, but always check before you graph it because it's really annoying to have to go through and erase parts of your line. Okay, questions on how I graph the line? And by the way, if you don't like this method of intercepts, you can always go back to the other method of solving for y, plotting the y-intercept and using the slope to graph the next point. Okay, now that's step 1. We drew our line. Step 2 is choose a test point. So we need to figure out which region is going to be a solution for the inequality. And I'm going to really explain this once we find the region, because I want you to understand what it is that we're doing. I'd like to use 0, 0 as a test point if I can. What I'm looking for is a test point that's easy to evaluate and a test point that's clearly on one side of the line. Now, the point 0, 0 is clearly on this upper left region of the graph. If I were to choose something like 5, negative 3, that would clearly be in the bottom region of the graph. It would also be a good test point, but 0, 0 is a lot easier to use. So we're going to test, in our case, 0, 0. And I'm going to determine if the region that contains 0, 0 makes a true statement. So I'm going to go back to my original inequality, and I'm going to let x be 0, and I'm going to let y equal 0. And I'm going to ask myself, is this inequality true? And when I take 4 times 0 minus 2 times 0, I get 0. And I get this statement, 0 is greater than or equal to 8. Is that true? No, 0 is not greater than or equal to 8. So this is not true. If it's not true, then don't shade that region. Shade the other region. So shade the region that doesn't contain 0, 0. If it was true, then we would shade the region that includes 0, 0. Okay, but 0, 0 does not make the equation or the inequality true. And because 0, 0 does not make the inequality true, I cannot include that region in my solution set. So when you're talking about inequalities versus equations, you're graphing solution regions. You're not graphing like, you're not having points that are solutions. So, or you're not getting a value at the end where you have x equals some number. When it's an inequality, you're getting a region as your answer. This is your answer. It's a graph. It's a line that's going to be either dotted or solid, depending on the inequality that you're given. And it's going to have one region of the graph shaded. Now, this is just one inequality. We're going to talk about systems of inequalities later. And in that case, you're going to have two inequalities, and you're going to have to tell me what region contains overlap. But this is how you graph a linear inequality in two variables. So you graph the line, pick a test point, and shade depending on what happened at your test point. Now, what this means is that I can pick any point in this shaded region, and it should satisfy the inequality. So, for instance, if you're thinking, well, what happens at the point 2, -4? If you're looking at the point 2, -4, that means that you should be able to plug 2, -4 into your inequality, oh, right here, and you should get a true statement. So 2, -4, 8 plus 8 is 16, which is greater than or equal to 8. Any point that you pick over here, anywhere, it could be, I don't know, negative, it could be positive 1,000, negative 1,000. Doesn't matter. As long as it's somewhere in this shaded region, it should make the inequality true. And it means that if you pick any point that's in the not shaded region, it's going to not make the inequality true. So we picked 0, 0. We saw it wasn't true. You could also pick 1, 1. 4 minus 2 is 2, which is not greater than or equal to 8. So you can pick any point over here, and it will not make the inequality true. And that's what we're doing when we're graphing inequalities. Now, the deal with the solid line versus the dashed is that when you have a solid line, you technically are going to solve the inequality on the line. And if you have a dashed line, then you cannot be equal to that line. So you can't use a point on the line as a test point. You have to pick something that's clearly on either side. Let's see. Oh gosh, Sebastian. Stick around for the office hour. Okay, so let's do one more, and then, okay, let's do one more, and then we'll be done until Monday. So let's do this one. 2x plus y is less than -5. So in this case, when you graph the line, you're going to have to graph it dashed or dotted if you want to do it that way, because you don't have the equal to in the inequality. Now, also, I might suggest if you don't want to do intercepts for this one, you don't have to, because y is already by itself. So you have a little bit less work to do if you just want to say y is less than -2x minus 5. So you can subtract the 2x from both sides, and then you could graph it using the slope-intercept form, y equals mx plus b, where m is the slope and b is the y-intercept. So your y-intercept is 0, -5, because the x coordinate's always 0 at the y-intercept. And you have a -5 here, or -5, which is really plus -5. And then your slope is -2, which is also -2/1. So we haven't done this in a while. That's your rise over run. If you want to do intercepts instead, be my guest. You pick. Okay, so I'm going to graph the line. I have a y-intercept at 0, -5, and I have a slope of -2. When your slope is negative, it means your line goes down from left to right. So the rise over run is 2/1. In order to get that to go down from left to right, I need to go up and to the left. I think that looks good. And then it's a dashed line because it's a strict inequality. There's no equal to in there. The slope looks like it got a little funky in there somewhere. Okay, questions about the line? The last thing we need to do is just pick a test point. I like 0, 0. It's clearly in one region of the graph over another. So I'm going to just pick the test point 0, 0. It won't always work. Sometimes you'll have a line that goes through 0, 0 and it won't work. But in this case, you can. I'm going to start out with my original inequality. 2 times 0 plus 0 is less than -5. And I'm going to see if that's true. Why do we have a parenthesis here? I don't know. I have 0 is less than -5. Not true. So I'm going to shade the region that does not include 0, 0. Okay. That's how you graph linear inequalities in 2 variables. And that is all. So I'm going to put up some homework for you from 5.4 and a teeny tiny bit of 5.5 to get started with, and then we'll finish this next time and we'll start 6.1. If you would like to make a copy of your 6.1 and 6.2 notes, please try to get that done over the weekend. If you have questions, email me. Your drop date is on Sunday, November 8th. I don't know if there's a time limit, but if you're going to drop with a W, do it by Sunday. If you want to email me to ask me my thoughts on that, feel free, but it's very hard for me to give you an answer on that. I'll do my best if you really want me to. I'll be in the office hour for another 13 minutes. Have a wonderful evening and a wonderful weekend